In this section, we'll talk about a technique which will allow us to reverse the process of squaring. Sometimes we need to undo that squaring process, and let me show you a circumstance that might involve that idea. If we have a square that's 4 feet on a side, we know that to find the area, we use the area formula, and we replace s with 4. 4 squared is 16. Now, suppose we have another square, and we don't know the sides, the lengths of the sides, but we know that the area is 36 square feet. You see, is there some mechanism for us to discover what number squared will give 36? We can probably think about the number and think that it's got to be 6, you see, in this particular case. But there must be a way mathematically for us to make that request, and that's what we're going to talk about. All right. Take a look at this pattern. Now, this is just a pattern which we're already familiar with. 1 squared means 1 times 1, which is 1. 2 squared is 2 times 2 is 4. 3 squared, 3 times 3, 9, and so on. Now, when we're squaring, you know, we have two equal factors that come from the idea of the exponent. So the exponent says that we have two factors of the base. We multiply those factors and we get a number. Now, the number that emerges out of this is called a square. Now, all of these are squares, you see. And if I continue the list, they would all be squares. Now, here's an interesting situation. 5 squared means 5 times 5, 25. Negative 5 squared means two factors of negative 5. Negative 5 times negative 5, also 25. So, there are two numbers, actually, which when squared will give 25. The numbers that are over here that are squared to produce these squares over here are called square roots. These are all, the bases of these exponents are all square roots of those squares. So 25 has a square root, which is 5. And another square root of 25 is negative 5. So that's how this whole mechanism works. And here's what we want to be able to do. We want to kind of be able to work this kind of backwards. Now, if the square that's over here is 25, we already know how we would proceed sort of in this direction. We know that we could have either two equal factors which are 5 or two equal factors which are negative 5 in order to get the 25, in order to produce this product to give 25. And we could write it in this base exponent form to identify the value of the square root, or I should say square roots. Could we do it for 49? Sure we could. We could think of 49 as 7 times 7, or as negative 7 times negative 7. So both 7 and negative 7 are square roots of 49. And then we could think about it for 81 and for some other numbers. Now, if we can think about it like that, then let's talk about the square roots of 36. And what we're doing is trying to identify those numbers which, when squared, will give 36. And from our experience, we know that 6 times 6 is 36, or 6 squared is 36. So 6 then is a square root of 36. We might write this. We might say, since 6 squared equals 36, 6 is a square root, I'll abbreviate a little bit, square root of 36. See, that's what we're thinking. But it's also the case that negative 6 squared is 36. So negative 6 is also a square root of 36. So the two square roots of 36 are 6 and negative 6. Now, and here, find the square roots of 64. Well, we know that 8 times 8 is 64. So since it is the case that 8 squared equals 64, and also negative 8 squared equals 64, since that's true, then 8 and negative 8 are the square roots of 64. All right, so that's the idea. Now, the request for square roots is made by using a symbol, a little mathematical symbol, and it looks like this. It's almost like a division sign, but it's not. It's a little wiggly thing here, and this symbol is called a radical sign. And the number that is under the radical sign is the radicand, it's called. And we're not going to use those words a great deal, but we will from time to time. Now, this symbol can be thought of as simply a request for a square root of 25, a square root of whatever the radicand is. It is a request for equal factors. You see, two equal factors that will give that number, that radicand. And it is more specifically than that. You know that there are two square roots for 25, but it's the request for the principal square root of 25 or the positive square root of 25. That's what this is the request for. If you want the negative value, the negative 5, then you would just put a minus sign out here. All right, so the square root of 25 is 5. The negative square root of 25 is negative 5. So here's how we ask for the two square roots of 25. You see, and we get 5 and negative 5 as the result. Now, I want to make sure, since we have a minus sign involved in this little process, I want to make sure we understand the difference between putting the minus sign out here and putting it under the radical sign. If the square root of negative 25 is a request for two equal factors that can be multiplied to give negative 25. Is there any such number that we can multiply times itself to get a negative result? No. No way that because if we're talking about two equal factors, then they're either both positive or both negative. And in both of those circumstances, when we multiply, we get positive results. So this is just not a possibility. So we say this is not possible. Now, if the number under the radical is not a square, then the square root of that number, the principal square root, is not going to be a whole number. And in that circumstance, we need to use the calculator to approximate the value of the square root. And here's how we do that. Suppose we want to approximate the square roots of 5. Well, to do that, we would use the calculator this way. We would use this square root symbol. Now, I'm calling it a square root symbol, but really it's used for other purposes besides just finding square root. So I'm using, we haven't seen any other purposes, so we might as well call it a square root symbol right now. But it's used for other purposes, and technically I ought to call this a radical sign. But at any rate, we use this symbol, and then we press 5 and then press enter on some calculators. On other calculators, we press the 5 first and then this symbol. And in those calculators, a lot of times, square rooting is an immediate response function. That is, the calculator will immediately make the calculation for this. On the kind of calculator where we would use this, we would have to press enter for it to perform the operation. All right, so that's the idea. Now, in the calculator, we get a very long decimal. And by the way, the exact value for the square root of 5 is a never-ending and never-repeating decimal. So this actually goes on and on and on. The calculator, though, has available only a certain number of characters, so we might get a decimal like this. Well, we would like to approximate the square roots of 5, so we would round off to some pre-designated spot, and I've chosen to round off here to the nearest hundredth. So to the nearest hundredth, the square roots of 5 are 2.23 and negative 2.23. And symbolically, we can say then that the principal square root of 5 is 2.23, and the negative square root of 5 is approximately negative 2.23. So that's the idea. Now, let's talk about how this might be useful in problems and how algebraically we might go about thinking about using the notion of square root. Suppose we know that x squared is 25, and we want to find the value of x. It's like saying we're requesting here, or we're wondering what number replaces this x so that the number squared will give 25. Well, gee, that is the exact request in using that square root symbol. So would it be, I mean, we can imagine that the numbers that could replace this x would be 5 and negative 5. Because if we square 5, we get 25. If we square negative 5, we get 25. So could we not make the same request here by saying that x then must be plus or minus the square root of 25? You see, and plus of the square root of 25 is 5. Principal square root of 25 is 5. So the x's that will replace this x to make this statement true would be 5 and negative 5. All right, now I'm kind of belaboring this point just a little bit, but I want to make sure we know how to think about this, maybe in 2 or 3 different equivalent ways. That if x squared is 25, we're looking for the number which when squared is 25, and that request is made using the square root symbol. That's the most important idea. Now this process, this algebraic process here, going from this step to this step, you might say that what we're doing is we're taking the square root on both sides. The square root of x squared is x, and we want both the positive and negative square root on the right side. So that's the idea. Okay, and for x squared is 49, same idea. Now sometimes this is called the square root property mathematically, that whenever we have a variable squared, then the variable which is squared is equal to plus or minus the square root of the number over here. No matter what the number is, no matter whether it's a square or not a square, it's okay. So here we would have plus or minus the square root of that number. Oh, it's a square. Square root of 49 is 7. So plus or minus 7. Now, suppose the number over here is not a square. Suppose it's a number like 5. If x squared is 5, then x must be plus or minus the square root of 5. We approximated the value a few moments ago to be 2.23. So x up here could be replaced with plus 2.23 or minus 2.23. That's what this plus or minus means. It means we really have 2 numbers being represented here. A few hundred years BC, there lived a Greek mathematician named Pythagoras. Pythagoras' father was a merchant sailor, and Pythagoras enjoyed mathematics. Well, Pythagoras had a chance to travel with his father, and as a result was able to encounter some of the greatest mathematicians of his time. And he learned from them, and he studied from them, and he studied all over the known world at the time. Well, Pythagoras came up with a very interesting situation. Actually, he didn't come up with it, but he was the first to publish it, so he gets credit for it. But here is the situation. Now let me lay it out this way. This is a little background, and I'll tell you about Pythagoras' idea or his theorem in just a minute. But notice that I have a right triangle here, and I have labeled the lengths of the sides. Here's what I want you to notice, that this side, now remember the side opposite the right angle is called the hypotenuse. If I square the hypotenuse, if I square the 5, I get 25. If I square this leg, 3, I get 9. If I square this leg, 4, I get 16. But notice this, that 25 is equal to 9 plus 16. 16 and 9 is 25, you see? So these are equal to one another. And we can kind of backtrack here and say 5 squared is equal to 3 squared plus 4 squared, or we can say that the hypotenuse squared, generally, is equal to the sum of the squares of the 2 legs in a right triangle. And that's what his theorem is all about. I'll tell you that I want to suggest to you that you kind of have a look at an illustration in your textbook. There's a really neat little drawing about a square that is a physical square that's made on this side and on this leg and up here on the hypotenuse. And you can see that the area of the square right here plus the area of the square that's right down here is equal to the area that's given by the square up here on the hypotenuse. So it really is a nice little connection in this relationship. Well, the Pythagorean theorem is this, that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the legs, and if the right triangle is labeled as ABC, as I've labeled it here, with the hypotenuse as C, it's C squared is A squared plus B squared. Now, it's important to recognize all of the time in right triangles that the hypotenuse is the longest side of the triangle and that it's always opposite the right angle. Those are 2 really important ideas in getting your head into problems involving the Pythagorean theorem. Now, consider this problem. Suppose I know that A is 3, B is 4, and I want to find C. And suppose I'm setting it up or I'm labeling it the way that I did the other one. That is, I know that C is the hypotenuse in this triangle, and I know it's a right triangle. Then to solve for C, and we already know what it is from what we did a little while ago, but to go through the solution, we would do this. We would say, all right, I recognize this as a right triangle. I'm going to use the Pythagorean theorem to solve for one of the sides. Don't care which side exactly when you just put down a general theorem like this. So you just replace the letters with numbers. Using this as a formula, you see, we're going to find the value of one of the sides, and we replace the a with 3 and b with 4 and just kind of follow our nose through it. 3 squared is 9, 4 squared is 16, 9 and 16, 25. So we have c squared is 25. But we know how to solve for c. You see, that it's this idea that some unknown quantity squared is equal to 25, so that unknown quantity, which is squared up here, must be plus or minus the square root of 25. Now, the only square root, there are 2 square roots for 25, you see, we know that. But the only one that makes any sense when it comes to dealing with triangles is the positive square root of 25, because we're dealing with lengths of sides, and we don't think about negative lengths of sides of triangles, so c then is 5. All right, so that's the idea. Now, there are other ways to deal with the Pythagorean relationship here. And I want to show you that because it's shown in your textbook, and I'm going to give you a choice of how to think about or think your way through problems such as this. But if c squared is a squared plus b squared, and we just kind of generalize the idea of solving for c, we're pretending that we're looking for the value of c, and we're given the values of these rascals, then c must be the square root of all of this business. You see, that's the idea. So the hypotenuse then is equal to the square root of the sum of the squares of the legs. And we could think of this then as a formula for finding hypotenuse when we know the legs. And we could generate some idea for finding a leg if we know the hypotenuse and the other leg. And we could do that like this. Here's the relationship. Now notice I've swapped sides. It's usually c squared equals a squared plus b squared, but I've just swapped sides in order for me to solve for one of these legs and have the unknown quantity on the left. But suppose I'm solving for a squared. Well, I'll clear b squared, and I'll do that by subtracting b squared on both sides. Now the b squares go out over here, leaving a squared. So a squared is c squared minus b squared. If I'm solving for a, and I know that a squared is equal to this quantity, then a must be the square root of this quantity over here. You see, and what do these letters stand for? Well, c is the hypotenuse, and a and b are legs. So a leg is found by taking the square root of the hypotenuse squared minus the other leg squared. You see, so we could think of this then as a formula if we want to. I kind of like, though, the idea of remembering one thing and applying it to a lot of situations rather than trying to memorize a lot of different things that apply to all those different situations. Here's what I'm talking about. Suppose I have a right triangle like this, and it's labeled this way, and I'm trying to find the length of this side. You see, now, what I recognize about this, first of all, is that it's a right triangle, that the hypotenuse is given as 10, one of the legs is 6, and I'm looking for the other leg. Now, if I remember the formula for finding a leg, then I could write the formula down and solve it. But if I don't remember the formula, I can certainly do this. I can say that I know the Pythagorean relationship, and it is that c squared is equal to a squared plus b squared. Now, I'm not too worried about the labeling here. I'm going to make a substitution in a minute that'll take care of that. This is easy to recall, you see. And so I'll just fill in for, let's see, what's the label for the hypotenuse? Oh, it's 10. So I have 10 squared equals. Now, one of the legs is 6 and the other is x, and I don't care which one I put where. It won't make any difference here. If I let a be the 6, then I have 6 squared plus the other leg is x, so x squared. Now I'll look at this as an equation and I'll say, well, gee, I'd like to solve for that x. And to solve for that x, I'm going to go through the squaring process for these two numbers. Let's do that. This is 100, and 6 squared is 36. And we have this. Now, I'm going to isolate the variable term by subtracting 36 on both sides. (100 minus 36), oh, let's see, that's 64. And the 36's go out over here, leaving x squared. Well, if x squared is 64, and I'm trying to find x, then I know that x then is the square root of 64. Now I say, we talked about plus or minus the square root of 64, but remember, we're talking about a triangle, so it's the positive square root that we're after. It's the principal square root. So it is that we want the square root of 64 that is equal to x. And so x is equal to, let's see, the square root of 64. What number when multiplied times itself is 64? Oh, that's 8. So x then is equal to 8. Here's a special case involving a right triangle. It's kind of a special right triangle. It's a right triangle in which we know that two of the angles, these two angles are 45 degrees each. Now let's look at, let's just take this sort of at face value here. We have C and A and B. All right, fine. Let's label those sides. And what we know though is that this triangle is an isosceles triangle. Remember, isosceles triangles were triangles which had two of the angles are equal to one another, and when two angles are equal to one another, the sides opposite those angles are equal to one another, so these two sides are equal. Now, although I have this labeling of A, B, and C, I know that A is equal to B. You see, so in using my Pythagorean relationship here, I can say, gee, if these are equal to one another, then they can replace one another, so I can write, in place of B, I can say it's the same as A. You see, so I can write this as A squared. Now, this is a very general kind of development. I'm not using specific lengths of sides. We'll get to that in just a minute. But I want to show you a little manipulation here. If we replace the B with A, then we have A squared and A squared, or 2A squared. You see, I'm just bringing together these two like terms to give 2A squared. And I know if C squared is equal to this, then C is the square root of that. You see, the square root of 2A squared, well, a manipulation that we'll learn more about later is that if we have a product here under this radical sign, then we can separate the idea of taking the square root between the two factors. That is, we can think of this as the square root of 2 times the square root of A squared. Now, what's the square root of A squared? Well, squaring and square rooting kind of undo one another, you see. This is a number used as a factor twice. This is a request for the number which, when used as a factor twice, gives this number. It's got to be A, you see. So, the square root of A squared turns out to be A. And A was just one of those legs, and both legs are equal to one another, so we could say then that we can find the hypotenuse. If we have a 45-degree angle for one of the angles, the other one's got to be 45. We've got two 45-degree angles, so we can always find the hypotenuse knowing a leg by just multiplying the square root of 2 times the leg. Now, this is a lot of development here to get to some little formula for a very special case. And we can use this, though, as a formula, and we could use it like this in a situation such as this one. Suppose we have a right triangle labeled this way, and we have only one side labeled, and we want to find the other sides. If it's labeled this way, though, we know that this labeling on the angles means that the angles have the same measure. And we know if it's a right triangle, you see, and those have the same measure, the sum of these two is 90, and therefore each one of them must be 45. So we can apply this idea that we just developed if we want to. Now, if these are both 45, those sides are equal. If this is 26, then this must be 26 as well. All right, and away we go. So C then is the square root of 2 times the leg. The leg is 26. Multiplying here, presumably using a calculator, we approximate C to be 36.77, and it would turn out to be meters. Now, if we don't wish to use this or memorize this relationship, we could memorize it, fine. Suppose we don't memorize it. Suppose we just go back to the general idea of this Pythagorean relationship involving the sides of right triangles. Well, we could proceed this way. Now, let's label this C because that's what we're looking for. And we would start with just C squared is A squared plus B squared. A and B are the same, no big deal. A is 26, B is also 26. Squaring 26, we get 676, and this is 676 as well. Collecting these two, we get 1,352. If C squared is equal to this number, then C must be the square root of that number. Using the calculator, we find C to be approximately 36.77 meters as expected. Here's a situation that may require a little bit of memorization. Now, to help you remember this, though, and it's just a relationship involved with the sides of a special right triangle, a triangle that has some special angles involved in it. Now, we looked at the situation with 45-degree angles, but we said, you know, we really don't have to memorize anything there because we can just go back to our fundamental idea of the Pythagorean relationship. Well, this one, though, might be a little special case. I'm going to show you, though, a diagram and a little development here to help you remember the idea. All right, here it is. Suppose we start with an equilateral triangle. Now, with equilateral triangles, you know all the sides are the same length and all of the angles are the same size. Now, this is 60, that's 60, this is also 60. I haven't labeled it, though, because I'm going to do something special up here. Now, all the sides are the same length, and let's just arbitrarily pick a length. Oh, I'll call it 10. 10 units of any kind. This is 10, this is 10, this is also 10. But here's what I'm going to do. I'm going to take this angle up here, and I'm going to divide it into two equal pieces. It's called bisecting. I'm going to bisect that angle. Now, if the overall angle was 60 degrees and I divide it into two equal parts, then each of these little angles up here is 30 degrees. Now, it turns out that in bisecting this angle and dividing the angle into two equal parts, when I extend this segment down to this side, it'll turn out that that segment will intersect this base of the triangle with a right angle. There'll be a right angle formed here, and not only that, that this point will be midway between these two vertexes, these two vertices. And because this point bisects or divides this segment into two equal parts, the overall side is 10, but this part of it is 5. Now, here's the interesting thing. The triangle is one where the angles are 30 degrees, 60 degrees, and 90 degrees. And in this circumstance, the hypotenuse of this little right triangle, the hypotenuse is 10, and this bottom leg, the short side of the right triangle, is 5. And that's always going to be the case. If I had chosen this to be 12, then this would be 6. If I had chosen this to be 50, this would be 25. So this side, this short side, is always going to be half of the hypotenuse. Or we could say the hypotenuse is always double the short side. You see, that's the idea. And the short side is always going to be opposite that 30-degree angle. So there are a lot of things that we can kind of look at here, but this is the special triangle that I'm talking about, one which is a right triangle. It's a 30, 60, 90-degree triangle. So we can write this relationship. We can say that in a 30, 60, 90-degree triangle, and it's a right triangle because of the 90 degrees here, but in this kind of triangle, the short side, which is the side opposite the 30-degree angle, but it's always going to be the short side. The short side is half the hypotenuse, or we could say that the hypotenuse is double the short side. Now, that little relationship might come into play in a situation like this. We have a triangle here. It's a right triangle, and we have only one angle labeled. It's 60 degrees. But we can figure out this other angle, can't we? After all, we know that the sum of the measures of the angles in a triangle is 180. And we also know that the sum of these two angles in a right triangle is 90. So using either of those ideas, we can find out that this angle is 30 degrees. And then, we have that very special triangle, that 30, 60, 90-degree triangle that we talked about. And so there is a relationship between the length of the hypotenuse and the length of the short side. Now, we can just step back and look and see where the short side is. Oh, it's this side. It always happens to be the side opposite the 30-degree angle. And in fact, generally with triangles, the shortest side is opposite the smallest angle. All right. So, let's see, with that relationship, this double half relationship, we see that, okay, this is going to be twice that. Okay, let's just write that down. The hypotenuse then is 2 times this leg. You see, and that's all there is to it. So C then is 8.6 centimeters. All right, that's the idea. Most of the time, though, all we do is apply the Pythagorean relationship in problems. Here's a word problem where we apply the Pythagorean theorem. The base of a 25-foot ladder is 9 feet from the side of a building. When the ladder is leaned against the building, how far from the ground is the top of the ladder? You see, and all we need to do really is draw a figure relating this idea, and we'll see the right triangle involved. Now, don't laugh at my diagram, but it's over here. I've got a ladder here, and it's leaning against what should be a building. All right, this is a building, let's pretend, and this is the ladder, and it's 25 feet long, and the base of the ladder is 9 feet from the building. All right, so that's the idea. And we're trying to find out how far up the building we can get with that ladder. How far will it reach up the building? You see, that's really what this is asking for. Now, we just need to recognize that the building makes a 90-degree angle here with the ground. You see, so that's the idea. Now we have a right triangle, and we have one leg is 9 feet, and the longest side here, the side opposite the right angle, is 25 feet. Oh, that's the hypotenuse of the right triangle. And so we just go about the business of popping in our Pythagorean relationship here among the sides of the right triangle and fill in the information we know. We know that C, the long side, is 25, so 25 squared. Now, if we label this side x, you see, then we have x squared plus 9 squared. And by the way, don't get confused here. These can be swapped around. I could call this side A and put the 9 right here, and I could call this B. I could just replace these. I could put the x over here and the 9 over here. It doesn't make any difference, all right? So there's nothing magical about putting x right here. All right, let's go forward. So I put the x here. I put the 9 over in the other position. 9 squared is 81. 25 squared is 625. I'm trying to solve for x, so I want to isolate this term. So I subtract 81 on both sides. 625 minus 81 is 544. The 81s go out on the right as expected. Bring down the x squared. If x squared is equal to this number, then x must be equal to the square root of that number. And we can approximate the value using a calculator, and it turns out to be about 23.3, 23 and 3/10 feet that the ladder will reach up the building.